For part A, we can use the equation that the energy is given by pi squared h bar squared over 2 ml squared, which is pi squared h bar is 1.055 times 10 to the minus 34 joule second quantity squared over 2 9.11 10 to the negative 31 kilograms is the mass, and the length is 0.5 10 to the minus 9 meters quantity squared. So this gives us 2.4 10 to the minus 19 joules, or 1.5 electron volts. For part B, we know that the potential energy is 6 times what we found in part A, so that equals 6 times 1.5 electron volts, or 9 electron volts. And now we can say that we can read the energies from the graph that's posted below as follows. This is 0.625 E1 IDW, which is 0.625 times 1.5 EV, or 0.94 electron volts. E2 would be 2.43, that much of the first energy, and that will give us 3.6 electron volts. E3 is 5.09 times that energy, which is 7.6 electron volts. The graph that I was talking about is the following. So we can see that E1 is 0.625, and E2 is 2.43, and E3 is 5.09. For part C, photon energy for n equals 2 and n equals 1. So E2 minus E1 is going to equal 3.6 electron volts minus 0.94 electron volts, which is 2.7 electron volts. And that corresponds to a wavelength of hc over E, 4.136 10 to the negative 15 electron volt seconds times the speed of light, all over the energy of 2.7 electron volts, which gives us a wavelength of about 460 nanometers. And lastly, for part D, the energy needed to free the electron from the well from n equals 1, U naught minus E1 is going to be 9.0 electron volts minus 0.94 electron volts, which is 8.1 electron volts, which is about 3 times the 2.7 electron volt photon energy in part C. Hence, the corresponding photon wavelength is 1/3 of the 460, or so 8.1 eV is approximately 1/3, 2.7 eV. So that means that lambda for 8.1 eV is approximately 1/3, 460 nanometers, which is approximately 150 nanometers, or in the ultraviolet range.